All right. So, do you guys like the numbering on here? So, oops, there's Maddie. Yeah, so I can follow my old answer key. And so I was like, if I renumber it, I won't know where my answers are. Anyway, you're all on the study set, either the one from Tuesday or the one from today, in case you haven't figured that out. So this is where we make an assumption. And this is the biggest point from the lecture from Tuesday, is how to make the assumption. So since it's molarity, molarity is moles of the solute, which is KCl, per liters of the solution, or total. So if it's this much molarity, we assume that we have 1.618 moles and 1 liter of the solution. So that's your assumption. And that is going to be if you have molarity. If you have molality, you make a different assumption. So just be careful of that. All right, so what are we solving for? Molality. So we're solving for moles of the solute per kilograms of the solvent. And again, if the solvent's not given, we say it's H2O. So the top part's easy. We have 1.618 moles of KCl. But the issue is how many kilograms of H2O do we have? And to find that, we have to do a subtraction step. So we'll do that over here. We have 1,000 milliliters of the solution, so total. And we know the density of the solution, so 1.234. Remember, a cubic centimeter is the same thing as a milliliter, so those just cancel. You can show your conversion of liters to milliliters. I just knew I was going to run out of space. So we have 1,234 grams. Now, just a reminder, don't label things as just grams with this. That is the key, is making your assumption and labeling more than just grams, more than just moles. This is grams, either total or of the solution. And again, do not abbreviate SOL. Hopefully you're not feeling like that. And yeah, so that actually stands for something. I am aware of that one. So we have to figure out how much water we have. So we know we have 1.618 moles of KCl. We can change that to grams. And which number is this? 13. KCl is like 74.6 grams per mole. And that will give us our grams of KCl. If you subtract the grams of KCl from the solution, that will give you your grams of H2O. And so that's the only way we can figure out the H2O is that step. So a quick comment about Sig Figs. The hope is you do somewhat respect them. I do get, though, that we all have different ways that our brains process. And so some people like to keep lots of Sig Figs. Your final answer, you do need to respect that we'll have 4, but technically this is all going to be place value. This would change to kilograms, so 1.113 kilograms, and that's how I got my answer, is from this setup would give me that answer. All right, for mole fraction, we're going to do, that's the X is going to be the moles of the solute, the KCl, over the total moles. No times 100, it's just going to be a number. So we know our moles of KCl is the 1.618. And then our denominator is going to again be the 1.618 moles of KCl. And then plus, we have to figure out our moles of HCl. So we had that many, you can figure it out separate, but you have that many grams of, I think I said HCl, of H2O, and then change your grams to moles, right? Periodic table, so 18-ish, blah, blah, blah. And mole fractions are always less than 1 because the total of the two. If you actually figured this out, just this comes out like 61.8 moles. comparing moles, it's such a huge difference. This is like 1.6 and this is 61.8. And so that's why this mole fraction comes out so tiny. All right, boiling point is change in temperature equals K times molality, or moles per kilogram. So moles of the solute. We actually figured out molality up above. And if an I factor is given, you do need to factor that in. So you would just plug in our molality from up above, the I and the K. A reminder, every compound has a different K value. KBs and KFs are not the same. And so I will give you the KBs and KFs. I know on one of these I forgot to, but it was one we used somewhere. All right, and you should get that the change in temperature is 3 sig figs, because the I does limit us, 1.37. Since it is H2O, we're going to increase the temperature, increase the boiling point. So the boiling point of water is defined as 100 degrees. That's actually the definition of degrees Celsius. And so that's how we can end up with 5 sig figs. Questions? All right, on number 8, so this one always confuses people, and it's because we cannot use this number, this formula, because it's an empirical formula. So we are going to still use delta T equals K times the moles per kilogram. I gave you a KB here. So we do our change in temperature, which is the change between those two, so 0.24 degrees Celsius divided by the K, right, which is the 2.53 degrees Celsius per molality, and then times the kilograms of the solvent, and that is the benzene. So times 0.030 kilograms of benzene. That's going to give you your moles of the anthracene. So of our unknown. Sorry, I had to look up what my number was. So 0.00285. So this is usually going to be our first step. Our second step is then we take the grams, which has, Christian, how many zeros did it have?
10.
Okay, there you go. Does anybody else have to count their zeros? Major, I'm like, sure you counted your zeros. All right, however many zeros you put there, make sure you got it right, because it doesn't matter. I just find that fascinating because it never mattered to me. And so it turns out I'm the one who's actually the oddball out, that more people have to count the zeros than not. And so that's why I put numbers like that, because I find it fascinating. And again, it's more me.
The part about it is,
what?
The part about it is searching a calculator, and if I get like a wrong answer, I have to delete all these 10 zeros and put them in again if I get a wrong answer.
I know, isn't that great? But you just have to accept that about yourself, and you have to laugh because you just have to do it, even though the best part is, Major, you know it doesn't matter. Because it's like, I mean, because it's after the, yeah, so now this is the part that is hard for students. Your temperature change here limits you to 2 sig figs. So for the moles, I often will keep 1 extra sig fig, but once I get to here, I can only say it's around 180 grams per mole. So this can only have 2 sig figs. Change in temperature, change in freezing point is a real hand waving. It's always an approximation. It's a lovely tool to approximate something. This is the molar mass. The reason we went through that, and so you have one of these on your lab. I did finally post your lab for Sunday. There you have a few calculations to do. You have some kitchen chemistry stuff to do, and you get to do another little essay. I made a video. I made it twice, so I got down to 21 minutes with some ideas, or you can Google your own. But it is, we need to pick topics, and so hopefully some people may have been inspired last week, or maybe this week you'll be inspired. And in the video, I give some topics that people have found in the past. All right. So now what we have to do is take the molar mass divided by the empirical mass. And so that's why the empirical formula was given there. So we have 180-ish grams per mole, and the empirical mass, it was C7H5. That comes out to like 89, I think. Yeah. Grams per mole. So when you add up on the periodic table, your 7 carbons and your 5 hydrogens. So this comes out that you're going to have 2 of them. So we double it, C14H10. So that's just more like a blast from the past from 221. And even a couple weeks ago, we had one like that. You're going to mostly just see like this, where it's going to ask you either solve for the molar mass or solve for the change in temperature or solve for the K. All right. But that just shows you how you can apply this to things that we've done in the past. Yeah, poor Yojenga. So our medic. All right, so that's his temperature, and that's the molarity, and that's our Bont Hoff factor, and we're doing osmotic pressure. So I just do it with PV equals nRT. We're solving for P, so we're going to divide by V, and remembering that moles divided by liters is your molarity. The I factor is anywhere you have the moles is where you're going to multiply it. So we're going to have to multiply by I, because the N is at that level. If we were dividing by the moles, then the I would be in the denominator. So we don't have to make an assumption, because I gave you 1, 2, 3, 4, 5, 6. You guys who like to count, that's a nice number. You don't have to worry about getting it wrong. Right. I have students who come back to me a year later, they send me an email and they tell me how much they miss my numbers, because they're like, yeah, I'm in a class now and the numbers are always like 22, or sorry, like 25. They're always like whole numbers. All right, molarity. I'm going to write my R out here. This is the true gas laws. This is the 0.82057, because this is ATM liters per mole K. So when we're doing osmotic pressure, the gas laws we were working in ATMs. Osmotic pressure is in ATMs. We use this R constant. I'm emphasizing that because I know where I'm going an hour from now, which is I'm going to teach you a new constant. And we have to make sure we know which one we're using. The temperature, what number is this, 7? 309.5-ish Kelvin. And we already got the volume is just 1 liter, because this was moles per liter. And then our I factor, 1.90. I has no unit, it's just a number. So again, sodium chloride, we all think when you put it into water, it's going to fully ionize into 2 ions. It doesn't perfectly do that. So you end up with 1.9 ions. So some of it stays together. Most of it comes apart. As you increase the temperature, the I factor goes up. So eventually it does fully dissociate. And you punch it in. And I will tell you this. It was a comment Christian made, not about this problem. I am blown. Osmotic pressures are always ridiculously high. I don't know why. But again, it's that attraction of the solvent for the solute. And so we call it a pressure, as if the solvent is being pushed, but it's not actually a push, it's a pulling of the solute, an attraction. Pushing and pulling always have to kind of happen together. And so pressure we usually think of, but these always come out huge. The one on the worksheet comes out ridiculously large, but that's just how osmotic pressures come out. All right, any questions on this first page? This was just some of the math. And most of you turned in the worksheet, and you all did really good with the worksheet on Tuesday. The worksheet today, you had to make some assumptions, but I think you'll all get it. And all right, number 9 is we're doing math again. So it's our temperature. All right, so are we doing a freezing point? I think so. Yeah, so change in temperature equals K. Oh, that's why this is the one that max, and then times I, because an I is given. I forgot to give you the KF on this one, but we did do one in our homework. So the KF, for anybody else who got stuck, nobody asked me, so I was assuming everybody had it. This is for H2O only. If I did something like that on the exam, I would hope somebody would ask me so I could, but I have been more cautious about making sure I do stuff like that. So like your worksheets, I worked them out and found anywhere I missed giving you that. KFs and KBs are different always, and every substance has its own unique KF and KB. So we just plug in. So our K is 1.86 degrees Celsius per molality. We're going to solve for X moles. We have our kilograms. Major, how many 3s are there? 3? 3 3s on that one? Okay. And
I don't think I'm ever gonna forget that, because I actually, like, when I was punching in the calculator again, I got a little bit annoyed. I was like, why did you just for like 2 of them?
I know, right? And you know I'm going to keep doing that. I do this every year, so don't feel too special, those of you who are like, why is she doing this to me? Because it's usually about the time I start to get to know the students, and this just has always amazed me. Be grateful that I don't write on the blackboard, because I don't erase well, and that drives students crazy. And so Major can tell you that when he was in my class and I used the blackboard. So the change in temperature, if it's water, your freezing point is 0. So the normal freezing point is 0 degrees Celsius. So whatever the new one is. And again, I do this as an absolute value. So I just keep everything as positive numbers. My change is 11. And so you're going to rearrange. You're going to solve for X. So X is 10.8, respecting Sig Figs. That is sodium chloride, and then you would multiply by the grams per mole. So our 58.5 grams per mole, and that's where I got, so it must be 630. I'm assuming that's 3 Sig Figs. Because this problem allowed us to have 3 Sig Figs. All right. Yeah, and I tried to highlight the part that you need to know. So for this one, which has the higher boiling point? So sodium sulfate is Na2SO4. A quick note, because some of you on the worksheet, you had the right answer, but you lost like a quarter point. This is 3 ions. So polyatomics do not break apart. So you have 2 sodiums ions plus a sulfate ion. So just be careful of that. So this is going to be 0.3 osmoles, or 0.30. So number of ions times the concentration. And then sugar is whatever it is. So it's just 0.15 osmoles. So this is not ionic. So you'll either see the word sugar, or I'll give you the formula of carbons and hydrogens. So which one has the higher boiling point would be the sodium sulfate. because it has more osmoles. All right, so the next one, ammonium nitrate, ammonium is NH4. That has a +1, and then nitrate is an NO3 that has a -1. So we just have 2 ions, ammonium and nitrate. So hopefully you have your little polyatomic list, because as you notice, I'm writing these out as words. So if you ran into something, or I guess Google will tell you, this gives us 0.6 osmoles. Sodium phosphate is Na3PO4. So that is 3 sodiums and 1 phosphate. So that is 4 ions. So again, the polyatomic doesn't break apart. So that gives us 0.6 osmoles. So they are the same. If it comes out the same, there's not going to be any difference. So it's not the concentration, it's not the number of ions, it's the combination of the 2 factors. All right, so number 12, this is how people make pickles. It's why when you go swimming in the ocean, you always, your fingers will always crinkle up and stuff. All right, so if you add 1 grain of KCl, it dissolves. That means it was unsaturated. There was room for more, so it did not have the max yet. All right. Diesel C12H26, that is non-polar because it's only carbons and hydrogens. And so miscible just means it's going to mix. You're looking for something that's like it. So C would mix with that. Ionic would not, and these guys are polar, right? We see the H bond, and that's polar. The chlorine would pull. So they're not going to mix very well. Let's see the next one. So it tells us 36 grams in 100 milliliters. So whatever the number is that it gives you, so we have 36 grams. This is our saturation point. So everything has a unique saturation point. Sodium chloride, it's not that high. As much as you see people add salt, the thing that's really fascinating is sugar. I've actually done this lab. I considered having you guys do it at home, but there is, like, I have the kids, they keep adding salt and mixing it until you can't add any more salt to like a cup of water. And then we did it with sugar. You can just keep adding. You can add like a whole bag of sugar to like a cup of water. Sugar and water love each other and they just keep mixing. It gets really thick and viscous. That's how they make like the rocks candy and stuff. All right, so if you take 22 grams in 77 milliliters, you would just have to figure out your ratio. Sorry. And so this comes out as like 0.285, which is going to be lower. So it is unsaturated. So she made a solution that was lower. All right. To make something more soluble, they like a low temperature. So this is gases like a low temperature, but they like high pressure. The thing that's interesting here is this is the exact opposite answer of how a gas acts ideally. So gases actually normally like low pressure and high temperature, but to get them into solution, you're going to have to push them in there. And so you put them under high pressure to push them in there and you keep the temperature low. So think about Coca-Cola. People chill their soda and that makes it more bubbly. A lot of cultures don't like cold soda because they don't like the bubbles. But in this country, you shouldn't be drinking soda anyway. Oh, there he goes. He drinks a soda right there.
It's sparkling water.
I know, I can tell that. But sparkling water has the CO2, right, in there. So They used high pressure and low temperature, makes it more sparkly. All right. So we're gonna make a colloidal mix. And he shines the laser through them, and what's gonna happen if it is a colloid, it's gonna scatter the light. So there you go, Major. When you go to work, you can bring a little laser on your keychain and shine it at the different solutions. All right, and okay, I have to always diagram this out. Can you guys still hear me? My headphones, I think my ears just popped or something. I can hear, I have not heard like this like the whole year, so something just happened. Maybe I'm going to hear God talk soon. This is going to be great. I wonder if, I don't know if you would get this. I was going to say, I wonder if he'll have George Burns' voice. That was a movie back in like the 70s. All right, so this is table sugar. And so pi. And does anybody know what 1.618 is that I keep using? Let's see. You can send me the answer. Somebody can tell me what that message is. Maybe I'll have to look in a moment. I can't, for my brain, this is like, so I kind of laugh at you guys. You have to count all the zeros. I actually cannot read the messages while I'm teaching. It like doesn't work for my brain. All right, so we have compartment A and compartment B. The thing is, for compartment B, it is sodium chloride. And so we have to multiply it by 2 ions. So it's not 1.618. So it's 3.236 osmoles. Sugar doesn't ionize. So these are not a big difference. However, we're going to get a flow towards the higher. So the water always moves, the solvent moves to the higher side. So again, the solute pulls it across. The sugar does not move, so neither moves. That's the key. The solute does not move. Unless there is a hole for it to go through, a door, the solute does not move. On B, the water is going to move from A to B. So it always moves to the side that has more because the solute is pulling it across. It's trying to dilute it so the two sides are the same. All right, so when the water moves over there, this side has less volume, so the concentration is going to increase. Does that make sense? So for on C, as you decrease the volume, you're going to increase the concentration. And so that's what's happening on for question C. All right, on question D, initially B is a higher concentration, so B is hyper. So hyper means above normal. And then E, the initially B, the higher solute is the higher osmotic pressure. You should call it something other than pressure because again, it's a pulling rather than a pushing, but any questions? Okay, we kept it. All right, I'm gonna stop and then